come now to the last exercise. So here we have an entire function. So this function is holomorphic and defined on the whole complex plane. And we know that the norm of this function doesn't grow too much. We know there exist these two constants, a and b, such that the norm of f is less or equal than a times norm of z to the n. We want to prove that this implies that f is a polynomial of degree at most n. The idea is to use Cauchy's formula. To prove that coefficients a k in the power series expansion of f at z0 equal to 0 vanish if k is bigger or equal than n plus 1. So we know that if f is an entire function, so f entire implies that f of z is equal to the sum for k going to 0 to infinity of ak times z to the k. And this is valid for all z in C. And now, from this formula, one sees easily that this ak is equal to the kth derivative of f at 0 divided by k factorial. And now, to estimate this ak, we need just to estimate the derivative, the kth derivative of f, and this will be done using the Cauchy formula. So, Cauchy's formula applied to gamma, which is a curve that parameterizes the circle of radius r bigger than 0 and center z0 equal to 0 in the anticlockwise sense. And so we have here the origin, and then we take this big circle parameterized by gamma. So this is a circle of radius r. And then what does the Cauchy formula says in this case is that fk, the point 0, divided by k factorial, this is equal to 1 over 2 pi I, the integral over gamma of fz over z to the k plus 1 dz. And now we want to estimate the derivative using this integral. So what can we say? We know that this number here, the norm of this number, which we recall this is also the norm of ak, this is equal to 1 over 2 pi, the norm of this integral. How can we estimate the norm of the integral? This is done using a formula that you learned during the class. using the length of the curve. So this is 1/2 pi times the maximum of fz divided by zk plus 1 in norm over gamma times the length of gamma. Okay, so what are these two? How can we now estimate these two elements, the maximum and the length? So the length we can compute it precisely. This is the length of a circle of radius r. So this is equal to 2 pi r. And now what about the maximum f divided by z? So here we know that z along the circle has a norm exactly r. So the denominator here has norm exactly r. So we can then write this as the maximum of the norm of fz times 1 over r to the k plus 1 times 2 pi times r. So if we simplify, we get 1 over r to the k times the maximum of f of z. Okay, and now we can use our hypothesis. So we know that this estimate here holds. And we can substitute it then here. So now using the hypothesis, we have that this is 1 over r to the k. And then here we have the maximum over gamma of a z to the n plus b. And now, once again, the norm of z over gamma is equal to r. So this is now equal to r to the k, r to the n plus b. So now we have this estimate, and what we do, we let r go to infinity. So if now k is bigger or equal than n plus 1, we get r to the n plus b over r to the k. This is equal to a times r to the n minus k plus b times r to the minus k. And both these quantities are negative now. So this number here, as r goes to plus infinity, converges to 0. So we find that the norm of ak is less or equal than the limit for r converging to plus infinity of this quantity, which is equal to 0 if k is bigger or equal than n plus 1. So the norm is less or equal than 0. This means that ak is equal to 0. So if we go back now to our formula for f, if all ak for k bigger or equal than n plus 1 are 0, this means that f is a polynomial of degree at most n. So this implies that fz is also equal to the sum until n of ak set to the k, and this is a polynomial. And we are done. So to recap what we did, we used the Cauchy's formula in this case. Cauchy's formula, you can see it here, gives you an estimate or compute the kth derivative of f, and in terms of an integral. And why is this useful? Because then this derivative gives us the coefficients in the Taylor expansion, the power series expansion at 0. So if we can show that these coefficients are 0 for k bigger or equal than n+1, we are done. And in order to prove this, we use the Cauchy formula to estimate the right-hand side here, using first the estimate in terms of the length and the maximum, this one here, and then finally using here the hypothesis on the statement of the lemma. And now, once we have this quantity, it's easy to see that for r going to infinity, this quantity goes to 0 if k is bigger or equal than n+1. And so we are done. So this is a proof that it's a bit different from the proof you find in the PDF file, but it's the idea is actually very, very similar, and both are good.